This number that we have stumbled upon, 6.022 times 10 to the 23rd, is actually called Avogadro's number. It's named after Amado Avogadro, who was the guy who originally had the idea that this should work. Avogadro felt that there had to be a number of particles such that if you took that many grams of a substance, that if you had a grams equal to the number of AMUs, there would be a known number of particles, and it would be the same for every single substance. And he was right. Unfortunately, he didn't live long enough to find out that that magic number was 6.022 times 10 to the 23rd, but they named it after him because it was his idea to start with. So some examples of that would be, because sodium has an atomic mass of 22.990 AMUs, and that's the mass of one sodium atom, Avogadro's number of sodium atoms weighs the same, but in grams. Since one water molecule weighs 18.015 AMUs, 18.015 grams of water contains 6.022 times 10 to the 23rd water molecules. So grab your periodic table and figure out how much Avogadro's number of iron atoms would weigh, how much Avogadro's number of sugar molecules would weigh, and how much Avogadro's number of wax particles would weigh. All right. Can anybody confirm that I did a good job adding?
Yes.
Awesome. Okay, so that's how we make use of Avogadro's number. So let's try an example problem. I have in a cup 46 grams of sugar. This is the amount of sugar in a can of A&W root beer. I just looked on the side and it said 26 grams, so here you go. This is the amount of sugar that is dissolved in one can of soda.
Wow.
It's a little bit horrific when you actually see it sitting in the beaker rather than dissolved in the soda, but there it is. 26 grams.
Sugar can soda.
You might as well just scoop this up and eat it with
That's the way we do it.
And this is in a can. Most people now buy a bottle, which is a much larger container. So this is just like your little 12-ounce can. So I would like to figure out, in my beaker full of sugar here, how many sugar molecules do I have? So the mass of sugar in one can of root beer is 46.0 grams. I would like to know how many molecules of C12H22O11 are in 46.0 grams. What I know from up above is that Avogadro's number of sugar molecules weigh 342.297 grams. So, do I have Avogadro's number in my beaker? No. That would be a lot of sugar. That would be 342 grams. So I have fewer than Avogadro's number worth of sugar particles, but I probably still have plenty. So 6.022 times 10 to the 23rd molecules of C12H22O11 would weigh 342.297 grams. So I know I have fewer than that. And now we have this nice shortcut that lets us go from grams directly to molecules. So I'm not going to have to stop at AMUs anymore. I bring down the 46 grams from my problem. 342.297 grams of sugar will contain 6.022 times 10 to the 23rd C12H22O11 molecules. So when you drink a can of soda, you consume 8.09 times 10 to the 22nd sugar molecules. And as we expected, it's fewer than Avogadro's number, but it still seems to be great plenty. Yeah, still a lot. Now, we are going to need to eventually get to the point that we have some kind of rules about how much stuff out of my calculator do I want to keep when it's time to actually write something down on paper. And that actually was going to be today and tomorrow's lesson, was to get that figured out. But if I spent today and the next cycle doing that, we were going to finish the semester in a really awkward spot. So I'm going to give you some real simple rules. And at the start of second semester, we'll come back and we'll figure out more specifically what exactly the rules are and why. So here's our very simple set of rules. 46.0 has 3 digits. When you give me an answer, give me 3 digits on your answer. Okay, it's going to be kind of our very simple rule. However many digits there are in the number you start with, just round to that many digits when you get all done. If you don't get the rounding and the proper number of digits exactly right, I'm not going to worry about it. But that just gives you kind of a ballpark for what exactly it is that I want you to do. On the back of here are 3 more things that you're going to do. The first one is going to be a nail. You're going to pick up a nail and you're going to figure out how many iron atoms there are in a nail using Avogadro's number. The second one, we are going to do portraits of me. So portraits of your chemistry instructor. How many wax particles are in a picture of your chemistry instructor? I sent a reminder this morning to bring crayons, but I have plenty if you didn't bring your own crayons. You are going to take a fistful of crayons and weigh them. Then you're going to draw a picture of me and then weigh them after you're done. Now, you can take this kind of from whatever angle you want to take this. I'm going to show you some from the past here so that you get the idea that perfection is not all that critical. Okay, so here, stick, Mrs. Dorner. I don't even know what this is supposed to be, but I apparently have a blue heart tattoo on my cheek. I know what this group thought of me, but it is kind of reminiscent of the book Where the Wild Things Are. The little dancing guy makes me think of the Where the Wild Things Are book. I thought this was really clever. Dr. Jekyll and Mr. Hyde. Okay. Clever. This group got their whole picture done, and they couldn't figure out what the problem was. They forgot something. Arms. So then they decided it was sleeping bag, Mrs. Dorner. They just wrote Z, 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 and said I was in a sleeping bag. No, a couple years farther back than that. Zelensky, I think. Buff, Mrs. Dorner? Okay. I think this was Hank Larson. He obviously visualized me as being much stronger than I actually am. And just to show you that no matter how bad the picture comes out, I could still possibly like you, my own child's rendition of it. Okay. Jack didn't even grant me the entire sheet of paper. He ripped the paper in half first, and then this is how I came out. Now, last year's pictures will always be a little near and dear to me because of the strange circumstances of last year. Last year, I kept having on a mask. Nobody had ever seen my face, so the bottom of my face was always either just a red or a black Nina mask because never ever were the masks off last year. So the poor group last year either had masked Mrs. Dorners or they just kind of had to imagine what might be there. So that was fun too because people just had to try to kind of think about, well, I wonder what Mrs. Dorner looks like underneath her mask. So you're going to draw a picture of me and figure out how many crayon particles get deposited on the paper as you draw a picture of me. The last one is how many water molecules in a gulp. You can define gulp however you want. You can drink it either out of your water bottle, or I've got a little paper cup if you need one. You're going to need a bigger balance for that part. So right back here, here's a balance big enough that you can actually just put your water bottle on it. So you can put your water bottle on it, take a big old swig of water, put your water bottle back, and you'll be able to figure out how much water is in a gulp. So that's going to be your next little task, is to figure out how many particles in each of these things. The nails are right over there. You'll have to scavenge the balances from your little blue tub, and you can get to work. Paper and crayons are in the back. Please put away your board, clean up your boards and put them away as you head to get your nail. And here is our nail. We can't really do the rest of it with you from home, but the nail weighs 1.36 grams. 1.37.
Our scale isn't there.